the Central Limit Theorem explained in plain English. So when you're learning the Central Limit Theorem, this is usually what you see as the mathematical statement. Basically, you get IID sample from a distribution with a mean, mu, and variance scheme square, and the x bar n is the sample mean, and then Zn is kind of the standardized version of the sample mean, and then when the sample size becomes really large, the distribution of Zn will be very close to the distribution of Z, which is the standard normal distribution. And yeah, at the bottom of the slide, you can see another way to express this relationship as the limit of the CDF, the cumulative distribution function of Zn, will converge to the CDF of the standard normal distribution. Okay, so this is the mathematical form of the CLT, but what exactly does it tell us in plain English? Now, first, let's just tone down a little bit. Let's restate CLT in the form of the sample mean. So it basically says the distribution of the sample statistic or sample mean is nearly normal, centered at the population mean, and with standard deviation equal to the population standard deviation divided by square root of the sample size. So underneath there, that's the kind of notation to kind of represent the statement. So let's try this. The CLT in plain English: if we repeatedly draw simple random samples from the same underlying probability distribution, then the sample mean is a random variable, which follows a normal distribution with the samples when the sample size is large. And this limit normal distribution has the same mean as the underlying probability distribution, and its standard deviation is the standard deviation of the underlying probability distribution divided by the square root of n, which is the sample size. Well, maybe this is easier to understand. But let's also make remarks on a few key points to help us understand the importance of the CLT. So key point 1, the CLT is one of the laws of probability. It shows certainty comes of uncertainty. Okay. And key point number 2, the CLT holds for, quote, any probability distribution. That means you can start out with almost like an arbitrary probability distribution, whether it's a binomial, it's counts, a uniform, or any skewed continuous, etc., etc. The end result of the sample mean will eventually converge to a normal distribution when the sample size goes large. So this is really, really powerful. And key point 3 is because of key point 1 and 2, the CLT has solved the problem of statistical inference of population mean or means for large sample size for any probability distributions. So only when the underlying probability distribution is non-normal and the sample size is small, usually we say n less than 30, do we need other statistical inference methods such as non-parametric tests. So this is really showing how powerful the CLT is. The CLT is the cornerstone of statistical inference.